Hello guys, welcome to lecture 7 of our lecture series Chemistry for Engineers. Today our topic will be on chemical bonding and molecular structure. In our previous lecture we looked at atomic structure. Today we will try to understand a little bit more as it relates to chemical bonding and biocompatibility of materials. Biocompatibility is the ability of materials to interact with biological system without triggering an immune response. There are different categories of biomaterials, such as metals, as we've seen in, for example, hip replacement, titanium metals, polymers, bioresorbable materials. Ionic and covalent bonds are very important in many bioengineering applications. Many bioengineering applications include ionic substances, for example, calcium phosphate. Calcium and phosphorus ions regulate the activation of osteoblast and osteoclast to facilitate the regeneration of bone. This requires that we understand electron configuration and chemical bonding. Understanding electron configuration helps us to understand at the level of the orbitals where electrons interact with electrons of different atoms. In our last lecture, we looked at energy changes in different types of bonding. We looked at ionization energy, which is the energy required to remove an electron. We looked at electron affinity, which is the energy required to accept an electron. These principles will determine whether we're dealing with a neutral atom, an anion, or a cation. The attraction of an atom for the shared electrons in a covalent bond is called electronegativity. When metallic atoms form cation and non-metal form anions, these oppositely charged particles produce ionic bond. The formation of an ion generally releases energy, as indicated by negative electron affinity, while formation of cation requires ionization. The arrangement of oppositely charged particles into a lattice results in a significantly stronger attractive force, so metals and non-metals routinely form ionic bonds. When bonds form between non-metal atoms, electrons are shared in pairs rather than transferred to form ions. The sharing of electrons in pairs is called covalent bond. Different atoms possess different ways of attracting electrons with covalent bonds. This is measured by electronegativity. The distribution of electron is not always equal or symmetrical, and this leads to the idea of polar bonds. Cell adhesion depends on electrical changes on the surface of the cell, and you call that polarity. A polar bond is a covalent bond between two atoms where the electrons forming the bonds are unevenly distributed. A nonpolar bond is a type of covalent bond in which electrons are shared equally between two atoms. The propensity of atoms to share electrons can be summarized visually in Lewis structure, which is why we have Lewis electron structures. By following simple rules, we can draw Lewis structure for many ions. We can also use the Lewis structure to predict the nature of the bonding involved. Lewis structure helps us to understand whether one or more pairs of electrons need to be shared, leading to the prediction of single versus double or triple bonding of molecules. But despite giving all this information, the Lewis structure doesn't really say much about chemical bonding because electrons are viewed as waves. When waves build up, they are said to interfere constructively, and the chemical implication is the formation of chemical bond. This orbital overlap can be manifested in different types of ways and can be distinguished by different types of bonds such as sigma bonds and pi bonds. Chemical bonds have structural implication as well because electrons are negatively charged. When there are several distinct bonds, they tend to be physically separated from each other. This idea gives rise to the geometry of molecules. This is called the valence shell electron pair repulsion, VSEP PR. Using the valence shell electron pair repulsion theory, the general shape of molecules and ions can be predicted. So here again, we can't escape the periodic table. We have the positively charged alkali metals, which are our group 1 elements. We also have the positively charged alkali earth metals, which includes our group 2 elements. Group 1 metals include lithium, sodium, potassium, rubidium, cesium, francium. These metals form 1+ charge. Our group 2 metals or alkaline earth metals form 2+ charge, which includes beryllium, magnesium, calcium, strontium, barium, rhodium. These are our transition metals. Chromium is able to form 3+ or 6+ charge. Manganese is able to form 2+ charge. Iron is able to form 2+ or 3+ charge. Cobalt as 2+ as well as nickel. Cadmium, zinc, mercury as well as plutonium. Gold can exist as a cation in a 3+ state. From the group 13 elements, aluminum as well. And here we have the anions, which include carbon -4, nitrogen, phosphorus, as well as arsenic that exists as 3-. And here we have oxygen, sulfur, selenium, tellurium. These exist with -2 charge anion. The group 17 elements, as we've met before in our last lecture, are the halogen, which include fluorine, chlorine, bromine, iodine, astatine. The halogens tend to form -1 charge. And here we have the neutral atoms, the gases such as helium, neon, argon, krypton, xenon, radon. So the Lewis structure is a simplified version of showing how many valence electrons an element has. So for example, hydrogen has 1 valent electron, helium has 2 valent electron, 2 in the s subshell. Lithium has 1 valent electron with an atomic number of 3. You would have 2 electrons that form the core electron, 1 electron in the 2s subshell. Beryllium will have 2 valent electron, boron will have 3, carbon will have 4. When the atoms combine to form molecules, a single bond is represented by 2 electrons. The halogens like to form 1 bond. Carbon has 4 valent electron, as we can see. It likes to form 4 bonds to get a total of 8, which satisfies the octet rule. The octet rule refers to the tendency of the atom to have 8 electrons on their outermost shell, or 8 valence electron. Nitrogen with a valence electron of 5 like to acquire 3. Oxygen with a valence electron of 6 like to acquire 2. Fluorine with a valence electron of 7 likes to acquire 1. So the elements on the right of the periodic table, or the anions, like to acquire electrons. The elements to the left of the periodic table are cations, and they like to give away electrons. Boron has 3 valence electrons. It doesn't really try to satisfy the octet rule, so it basically gives away 3. Beryllium has 2 valence electrons. It also doesn't satisfy the octet rule, so it basically likes to give away 2. So the number of valence electron corresponds with the number of bonds they like to form. Hybridization is basically the combination of atomic orbitals. So it's basically a combination of the s, p, d, f orbitals, as you can see here. sp3d2 means that there is 1s, 3p orbitals, 2d orbitals. 3p orbital comes in x, y, and z. So here you can see there is 1dx orbital as well as a dy orbital, or a dy orbital as well as a dz orbital. From replacement hip joints to heart valves to new lenses for eyes, the collaboration of chemistry and engineering annually provides medical miracles for millions of patients who needs to replace worn out or damaged tissues. Materials used in human body must be capable capable of many things, including having physical properties that are at least similar to the biological materials, such as bones, that they are replacing. So here we can see a list of biomaterials such as silicon, where a silicon rubber is used for a finger joint, silicones that is used for breast implant, stainless steel that is basically used for heart valve, titanium that is also used for hip replacement, polyurethane metal that is used for artificial heart, polymethyl methacrylate that is used for intraocular lens. Biomaterials can be classified such as metals, polymers, natural polymers, hydrogel, bioresorbable materials, ceramics, glass, and composite. Bone cement is described as a biomaterial such as polymethyl methacrylate. You have intramedullary nails that are used for fractures. You can also have cemented versus uncemented acetabular cup, which is basically used in hip replacement. Ultra high molecular weight polyethylene, which can be used in knee replacement. Transpendicular spine system, which is used for spinal injuries. Polymers are used for cartilage and tissue engineering, corneal, cardiac, as well as skin and bone engineering. And recall from our first lecture that polymers are a group of monomers, and the monomers are a group of molecules. The molecules are a group of atoms joined together. You have polymers in your body such as proteins, carbohydrates, lipid, nucleic acid. These are natural polymers. Synthetic polymers include polypropylene, polyethylene, polyvinyl chloride, polyester, polystyrene. You also have bioresorbable bone fixation plate, wireless bioresorbable sensor as well. Biocompatibility is the ability of a material to interact with biological materials without triggering an immune response. There are several strategies for achieving biocompatibility. In some cases, the key need is strong cement. The first bone cements used were based on polymethyl methacrylate, PMMA. The polymerization reaction, which goes to completion after the cement has been applied, causes the cement to harden. So here we have examples of polymethyl methacrylate applications, for example, in bone cement, contact lenses, intraocular lenses, screw fixation in bone, filter for skull, artificial teeth, filter for bone in vertebroplasty, stabilization. More recently, cements based on calcium phosphate or composite of calcium phosphate and calcium silicate have been developed. A number of smaller methods start with smaller molecules referred to as precursors and react them with each other or with the surface of the object to be coated. Choosing appropriate precursor for coating reaction requires knowledge of chemical bonding, not only in these starting with materials but also in the consultant coating. So here we can see a calcium phosphate based biomaterial. The calcium phosphate based material are synthetic materials used to reconstruct damaged bones. This also incorporates the bone healing process, where the calcium phosphate material degrades while the bone reforms or generally restores itself. So this basically leads to a programming of the bone forming cells, the osteoblast. So basically what it does, it causes a downregulation of inflammatory factors such as interleukin 1 beta and upregulation of various growth factors and other inflammatory factors. So the growth factors will help to stimulate the osteoblastic cells to remodel the bone. So the growth factors would include vascular endothelial growth factors, bone morphogenic protein, for example, and the inflammatory factors would include interleukin 10 and other variants of interleukin 1. Various gene regulation will cause the osteoclast to detect the calcium phosphate biomaterial, which will activate the breakdown or resorption of the calcium phosphate material. This will also lead to the osteoblast becoming activated to produce new bone or assist with the formation of bone. So basically what you're seeing is a synergistic effect where bone production is triggered by the calcium phosphate biomaterial. So naturally, this would help to heal or regenerate destroyed bone. Biomedical engineers must understand how biomaterials interact with cells in the body. Cell adhesions depend critically on the nature of electrical charges that is emitted from the surface of the cells, and you basically call this polarity. Polarity is important not only on the surface of the extended systems, but also in small molecules in the body, particularly water. So cell polarity allows the neighboring cell to respond to cues based on what is projected on the surface of the cell. This will help with cell migration, will also play an important role in which epithelial cells communicate, and with understanding more as it relates to cell mechanics, you will see that cells communicate via junctions. Cells are held together by anchoring proteins. This is also crucial for cell division or replication, and various proteins or chemicals or chemotaxin release will help to guide the cell as to how to respond to another cell or biomaterial in the environment. All chemical bonds arise from interaction of oppositely charged particles. The simplest example of such an interaction is found in an ionic bond formed through the electrostatic attraction of two oppositely charged ions. Many bioengineering applications include ionic substances such as calcium phosphate or calcium silicate. Cements include such bonds. So this is just an example of ionic bond, two oppositely charged ions, a cation and an anion, the Lewis structure for sodium and chloride, and we also have the electron configuration for each. Sodium has 1 valence electron, chloride has 2, 4, 6, 7 valence electron, as we've said before. So if atoms should bond, you basically have a transfer of 1 electron from the 3s subshell to the 3p subshell of chloride, which contains 5. Here you form a sodium chloride ion, so the configuration of chloride would change to 3p6. Ionic bonds can also act as precursor for growth of ceramic coating, but the important thing is you have to remember that ionic bonds form between a metal and a non-metal. So we saw where the alkali metal, sodium, formed a bond with the non-metal chloride, which basically produces a sodium chloride bond. It always has to be a metal with a non-metal. And the more different two elements are in their metallic properties, the more likely it is that a compound formed from these elements will be ionic. So again, ionic bond is when the neutral atom loses an electron. It has to be a metal and a non-metal will then form an ionic molecule. So ionic compounds usually consist of elements that are widely separated on the periodic table. So it's like the right merging with the left. And remember that we have energy change when an atom loses an electron. Ionization energy is required. When an atom gains an electron, electron affinity is required. And the number of energy, or the total number of energy in joules, is dependent on the subshell or whether the atom gains or loses an electron. So as you move up and across the periodic table, the ionization energy increases. As you move up and across the periodic table, the electron affinity increases. So here we have example of ionic bonds. We saw that sodium gives chloride 1 electron to form a sodium chloride molecule. Recall that magnesium likes to give away 2 electrons. So magnesium will form ionic bond with oxygen by transferring 2 electrons to form magnesium oxide. Lithium has 1 valence electron and forms an ionic bond with fluoride by giving away this electron to form a lithium fluoride molecule. Lithium can also form ionic bond with sulfide in the same way to form lithium sulfide molecule. Metals form cations and nonmetals form anions. In each case, the ion we find in compounds are those whose formation is not too costly in energy. So when a metal or a cation form a bond with a nonmetal or an anion, this doesn't result in a lot of energy. By looking beyond the first ionization energy, we can also see why some metals form 1+ cations, whereas others have higher charges. From lithium to fluoride, ionization energy increases. Sodium to chloride, ionization energy increases. From magnesium to sulfide, ionization energy increases. Calcium to phosphate, and so on. So for a filled p subshell, removing an electron will result in a large jump of ionization energy. This large jump in ionization energy explains whether the cation form will have a charge of 1+, 2+, etc. And this is just here to jog your memory. So here we have a decrease in atomic radius to this direction, an increase in ionization energy to this direction, an increase in electron affinity to this direction as well, an increase in electron affinity and ionization energy to this direction. These are our metals, these are our nonmetals. When we look at the progression of ionization energies for sodium, this is not surprising. So from the first ionization to the second ionization energy for sodium, 496. For the second ionization energy, 4,562 joules per mole is required. And the third ionization energy, 6,912 kilojoules per mole is required. And this is because sodium naturally occurs with a single charge. Predict the ions that magnesium and aluminum are most likely to form. We would expect 2 electrons to be removed, and the most commonly found ion should be magnesium 2+. For aluminum, the third ionization energy is 2,745 joules per mole, whereas the fourth is 11,578 joules per mole. We would expect 3 ionizations to occur, so aluminum should form aluminum 3+. Whenever you move an electron from the p6 subshell, it always results in a large jump in ionization energy. This large jump in ionization energy explains whether cation formed will have a large 1+, 2+, etc. For example, sodium occurs naturally only as singly charged or 1+. When we look at the progression in ionization energy for sodium, this is not surprising. The first, the second, and the third ionization energies for sodium are 495 or 496, 4,562, 6,912 kilojoules per mole, respectively. When we see the huge amount of energy required to take a second or third electron from a sodium atom, we see why that nature might choose to stop at only 1, because first energy to the second requires a large amount of energy. Using data from the table, predict the ions that magnesium and aluminum are likely to form. We would expect 2 electrons to be removed, and the most commonly found ion should be magnesium 2+. For aluminum, the third ionization energy is 2,745 kilojoules per mole, whereas the fourth is 11,578 kilojoules per mole. We would expect 3 ionizations to occur, so aluminum should form aluminum 3+. So because we move in 2 electrons from magnesium, we expect a large jump in ionization energy. Because we're moving 3 electrons from aluminum, there's a large jump in ionization energy. Our examples show the most common cation for metals in the S or P blocks of the periodic table is generally one with a P6 configuration. We have the S block and the P block here. Here we have the P6 P5, P4. Many transition metals form more than one stable cation. The transition metals have partially filled d subshell, but ionization usually begins with loss of electrons from the s subshell. When ions form 2+, for example, the electron configuration changes from 1s1, 1s2, 2s2, 2p6, 3p2, 3p6, 4s2, 3d6 in the neutral atom to 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. So basically 2 electrons were removed from the 4s orbital. In this case would be the highest energy level. The loss of one additional electron from a d orbital leaves Fe3+ with half-filled d subshell. This half-filled subshell is fairly stable arrangement, so the Fe2+ and Fe3+ ions are both stable. With many transition metals, the situation can be quite complicated. If we look at the periodic table for electron affinity, we see they are similar to those of ionization energy. Recall that electron affinity is the energy change for formation of an anion from a neutral atom. So this basically results when you add an electron to a neutral atom and it becomes negatively charged. From hydrogen to helium, there's a decrease in energy. From helium to lithium, there's an increase in energy. From oxygen to fluoride, there's an increase in energy. We already know that energy is released when the anion is formed. The amount of energy released when atoms acquire additional electrons tend to increase as we go from left to the right across the periodic table. Looking at this trend, those atoms that gain electron are most likely also would need to lose large numbers of electrons to produce cations with stable p6 electron configuration. Thus, nonmetals tend to form anions rather than cations. For the formation of anion from nonmetals, we do not find any of the complexities we encountered with the transition metals because all of the nonmetals belong to main groups and do not have partially filled d subshell. They behave like the main group metals in that they tend to acquire electron configuration with filled p subshells. The primary difference is that they do so by gaining rather than losing electrons. All the halogens form singly charged 1- anions, resulting in p6 electron configuration. Similarly, oxygen and sulfur form anions with a 2- charge, resulting in the same np6 configuration. In addition to the charge, the size of the ion ultimately has an effect on the strength of the ionic bond, largely due to the geometric constraints. Atomic radius increases going down a group and decreases going across a period. The loss of an electron to form a cation decreases electron-electron repulsion, leaving the remaining electron more tightly bound to the nucleus. So we would expect positive ions to be smaller than respective parent atoms. So atomic radius increases going down a group and decreases going across a period. Adding an electron to form an anion will lead to an increased repulsion among valence electrons. So anions should be larger than their corresponding neutral atoms. Ionic radii can be determined very accurately by measuring the spacing in crystal lattice, and data are consistent with these expectations. So this includes the size of atoms and their ions in picometer. With an ionic radius of 102 picometer, sodium 1+ is significantly smaller than sodium atom, which has an atomic radius of 186 picometer. The 133 ionic radius of the fluorine anion is significantly larger than the 72 picometer atomic radius of the neutral fluorine. And here we can see the atomic radius of the anions versus the neutral atoms, the cation versus the neutral atoms. So basically, the atomic radius of the neutral cations tend to be larger than the ionic component of each, while the opposite is true for the anions. So it basically shows that the atomic radius of the cation is smaller than the neutral atom. The atomic radius of the anion is larger than the neutral atom. When we compare similarly charged ion going down a group, ionic size increases in the same way that we saw for atomic size. For cations, the trend in ionic size going down a period also mimic the trend we saw for neutral atoms, decreases as we go from left to right. This is easily understood considering sodium 1 plus and magnesium 2 plus, for example. We see that both ions have the same electron configuration. Magnesium has one additional proton in its nucleus and so will hold its electron more tightly, leading to a smaller ion. We can apply the same sort of reasoning to the common ions in the p blocks. The oxide ions O2 minus and the fluoride ions F1 minus have the same configuration, but fluoride has one additional proton in its nucleus, and so it is the smaller ion. Similarly, chloride is slightly smaller. Starting with a neutral metal atom and a neutral non-metal atom, it will usually cost energy to form an ion pair, for example, a cation and an anion. Ionization energies are always positive, and the energy input to produce a cation from a metal is not offset by the energy release when an ion is formed from a non-metal, which we already know. Once formed, the oppositely charged ions will attract one another, leading to a significant lowering of the overall energy. Coulomb's law says that force between two charges is proportional to the product of the magnitude of their charges divided by the square of the distance between them. K is a proportionality constant whose value is 1.389 times 10 to the 5 joules picometer per mole. So the Coulomb's law gives the electrical force between 2 point charges. So we're basically looking at the oppositely charged ions and how they are attracted to each other by an electric force through the formation of energy. So K is the Coulomb's constant, 9.08 times 10 to the 9 or 1.389 times 10 to the 5 kilojoules. This would represent the charge of each ions and the distance between the two charges. So this is just a different way of representing the same thing, where you have the force times Q1 times Q2 divided by R squared. So F is the force, Q1 and Q2 are the charges, and R is the distance between them. In this case, the distance between the nuclei of the two ions. It can also be shown that the potential energy of the system is given by the force times Q1 times Q2 divided by R squared, which would be the distance between them. So Q1 times Q2 divided by R squared, which is the distance between them. And it basically is calculating the force between each. Let's look at a specific case by evaluating the energy change in the formation of a bond sodium fluoride ion pair from isolated atoms of sodium fluoride. The ionization energy for sodium is 496 kilojoules per mole. The electron affinity of fluorine is minus 328 kilojoules per mole. So we need to supply 496 kilojoules per mole to ionize sodium, but 328 kilojoules per mole will be released in the formation of fluoride ion. Combining these two numbers, we see that forming the individual ions will cost 168 kilojoules. So you minus the 496 from the 328, that would be 168 joules per mole. Next, you need to use the equation to determine the energy released by the coulombic attraction between the anion and the cation. The radii of sodium 1 plus and fluoride oxide 1- or 102 picometer and 133 picometer respectively, the internuclear distance should be 235 picometer. Inserting this into equation 7.2 as R and evaluating gives us the energy of attraction between the ions. So here we have the force, or the constant, of 1.389 times 10 to the 5 joules per picometer per mole. So the force between them are 1 plus 1 minus, and the distance between them is 235 picometer, which basically gives us a minus 591 kilojoules per mole. The negative sign indicates that the energy is released. Notice that the magnitude of the coulombic energy far outweighs the energetic cost, forming two ions. So the whole process we have described does release energy. So basically, if sodium fluoride was really formed, then it would produce a bulk crystal lattice made up of many ions. And this is where you get a physical structure. And in a lattice structure, the ions are attracted to every other oppositely charged ions. So at the same time, those with the like charges will repel each other. So the further apart they are, the weaker the attractive force. So here we have sodium fluoride crystal. The black lines show the attractive force between the first nearest neighbors. Red line shows the repulsive force between the second nearest neighbors. The blue line shows the attractive force between the third nearest neighbor. Here you have a repulsive effect. So this basically shows that in a lattice structure, you will have repulsive as well as attractive forces between the ions. The lattice energy of a crystal contains contributions from all of the attractions and repulsions. In the sodium fluoride structure, each sodium ion is surrounded by 6 fluoride ions, and each fluoride has 6 neighboring sodium atoms. To get an accurate indication of the coulombic energy of the lattice, we would need to account for the interaction of each ion with its many neighbors. The coulombic energy that we calculated was for 1. So basically, when you use a single pair, however, it underestimates the total energy of the lattice. The actual energy released in the reaction between sodium metal and a diatomic fluorine gas to produce solid sodium fluoride turns out to be 577 kilojoules per mole. So if the ion is small and highly charged, it will tend to form ionic compound with large lattice energies. If the ion is large with small charge, it will tend to form compounds with small lattice energy. So in the following pairs of ionic solids, the ions are arranged into smaller lattices. Which one has the largest lattice energy? Calcium oxide or potassium fluoride? Sodium fluoride or cesium iodine? So basically, when the ions are small, they tend to form stronger coulombic interaction because the distance between the nuclei is smaller, and ions with larger charges have a stronger interaction. So here we have the lattice energies for some compounds, and as you can see, for calcium oxide, the lattice energy would be 3,414 kilojoules per mole. For potassium fluoride, it would be 808. For sodium fluoride, 910. Cesium iodine would be 657. In calcium oxide, calcium exists as Ca2 plus and oxygen as the oxide ion, so O2 minus. In potassium fluoride, the constituent ions are potassium with 1 positive charge, fluorine with 1 negative charge. So because potassium and calcium are in the same row and they're both cations, the size difference between them is not too great. And the same is true for oxygen and fluorine. The size difference between them should not be that great. So calcium oxide should have the larger lattice energy because because the charges on its ions are larger than the charges on the ions in potassium fluoride. And in that case, potassium would be slightly larger than calcium as well, and oxygen would be slightly larger than fluorine. All the ions in this problem are singly charged, so the size difference must be the key issue. Sodium cation with 1+ charge, fluorine with -1 charge are smaller than cesium cation with 1+ charge and iodine with -1 charge. So the lattice spacing in sodium and fluoride must be smaller. So basically, sodium fluoride should have the larger lattice energy. So as we've said before, covalent bonds are based on sharing of electrons between two atoms. How does covalent bonding occur, and how does it influence the behavior of compound like polymethyl methacrylate cement? Covalent bond is not like ionic bond. Covalent bond is when they share electrons. So there's no transfer of electron. So you can have a polar, a non-polar, as we've said before. You can have a single, double, or a triple bond. So you basically have 2 electrons shared, 4 electrons shared in this case, 6 electrons shared in this case. So we know already covalent bond is basically when 2 nonmetals share electrons. So it could be hydrogen, oxygen, so gases, for example, or the halogens. But in the same way, the driving force behind the formation leads to lowering of energy. If the atoms are significantly far apart, they won't exert discernible force on one another. So here you can see the diagram showing how potential energy of a pair of atoms might vary as the atoms draw closer together and form covalent bond. The minimum in this potential well corresponds to the normal bond length and the bond energy for diatomic molecule. So here, when the atoms are widely separated, they do not interact with each other at all, so the potential energy is closer to 0. When the atoms are further apart, they do not react with each other, so the potential energy is closer to 0. So as the atoms approach each other, they begin to interact and the potential energy decreases, because as you can see, the energy increases to this direction. The attractive interaction lowers the potential energy. When the atoms reach an optimal separation, there is significant sharing of electron between 2 nuclei. The distance lowers the potential energy more than any other, and it's called the bond distance. So when they are closer and there is a closer internuclear distance between them, there is a force that is created between the 2 nuclei, and this even further lowers the potential energy. This basically results in what we call the bond distance. And when the atoms are pushed too close to each other, the nuclei start to repel each other, and there's a dramatic increase in the potential energy as a result. So when atoms are close enough to form a chemical bond, you have a significant amount of density that build up between them, between the nuclei, and the electron clouds are no longer spherical. So as the atoms approach each other, the negatively charged electron clouds become attracted to both nuclei. And when the atoms are widely separated, their electron clouds are not distorted by the presence of the atom and are spherical. So the closer they are together, the less spherical they become. This will also result in a significant increase in the electron density. Eventually, the electrons from one atom can become attracted to the positively charged nucleus of the other atom. This added attraction lowers the potential energy of the system. So we know that once the atoms come closer together, this results in a lowering of the potential energy. The 2 nuclei will repel each other naturally, and as do the bonding electrons, so the nuclei cannot approach too close to one another. This is basically just showing covalent bond between hydrogen atoms, and as you can imagine, the closer they are together, the more dense and the less spherical. Here we also have a hydrogen chloride bond where the 1s subshell is overlapped with the 3p subshell of chloride, and this forms a double bond where the electron from hydrogen is shared between chloride fluoride. And here we have a chloride-chloride bond where both 3p orbitals overlap. And the important thing here is that this satisfies the octet rule because chloride has 6 unpaired electron, and here we have 2 paired electron to form 8 electrons. At some point, a balance between these attraction and repulsion will occur. So the closer the atoms come together, at some point the balance between these attraction and repulsion will occur and the energy of the system is minimized. This point of minimum energy corresponds to the formation of a covalent bond. The energy released when isolated atoms form a covalent bond is called bond energy, and the distance between the nuclei of the bonded atoms is called the bond length. So here we have the potential energy in kilojoules, the attractive force, the repulsive force, the bond energy, which is the energy released when the atoms form covalent bond, and the bond length, which would indicate the distance between the nuclei of the bonded atom, which is also the internuclear distance. So the bond energy correlates with the potential energy, which will look more at the attractive force, but while the bond length will look at the distance between the nuclei and will correlate more with kinetic energy. When electrons are shared between two atoms, their distribution is different from that in the individual atoms. We see how electron density in a molecule differ from the spherically symmetrical distribution seen in isolated atoms. In a covalently bonded molecule, there is a buildup of electron density or a concentration of negative charge in the region between two bonded atoms. So this would be the region of electron density where you find the nuclei of the covalently bonded molecule, as well as the concentration of negative charge between each. And this is showing the electron density as well as the negative charge between lithium fluoride. And this is the density difference plotted on an axis. The increase in electron density need not be particularly large. Even a slight increase of negative charge in this region lowers the potential energy of the system and can stabilize the molecule. The formation of a chemical bond always releases energy. Once a bond is formed, that same amount of energy, the bond energy, must be supplied to break the bond apart. So the same amount of energy that is used to form the bond is the same amount of energy that is used to break the bond apart. The magnitude of this bond energy depends on the atoms involved. When two molecules of fluorine atoms combine to form 1 mole of molecular fluorine, 156 kilojoules of energy is released. So we say that fluorine to fluorine bond energy is 156 joules per mole. Compared to many other molecules, difluorine is held together by a relatively weak covalent bond. Chemical reactions involve rearranging bonds so that reactants are transformed into product. A reaction will be energetically favored if the energy required to break the bonds is less than that released in making new bonds. So biomaterials such as a Teflon mesh used to reinforce an abdominal wall after surgery are intended to replace or strengthen the tissue. Polytetrafluoroethylene is a fluorocarbon where you have fluoride atoms covalently bonded to carbon. So when you use this Teflon mesh for an abdominal wall surgery or to reinforce the abdominal wall after surgery, the Teflon has to be metabolized by combustion. So the biomolecules are broken down into H2O and carbon dioxide. And Teflon is a trade name for polytetrafluoroethylene, and a key property of PTFE is its resistance to chemical reaction. More importantly, notice that large differences in the strength, the oxygen and the hydrogen and oxygen and fluoride bonds. These bond energies show us that to burn a fluorocarbon, we would have to replace strong strong carbon fluoride bonds with weaker oxygen fluoride bond. Energetically, this is not at all favorable, and many fluorine containing molecules are not flammable. A simple look at bond energies can help explain the non-reactive nature of Teflon. This basically shows the bond energy of some types of bonds in important combustion of hydrocarbons and fluorocarbons. It shows that carbon to fluoride bond has a bond energy of 485 kilojoules per mole, carbon to hydrogen 415, oxygen fluoride is the weakest of 190 kilojoules per mole, while oxygen hydrogen bond is 460. So the carbon fluoride bond is very strong, as we said before, while the oxygen fluoride bond is very weak. We look at ionic bonding between metals and non-metal. We saw that the formation of cations and anions is consistent with achieving NP6 electron configuration that resemble those of rare gases. For non-metal atoms, a rare gas configuration can be achieved by gaining the electrons from metal atoms, leading to ionic bonds. Here we have the hydrocarbon, which has a tetrahedral shape. This goes into molecular geometry, and we have overlapping of the orbitals and shared electrons. Here we also have difluoride bond where two p orbitals overlap. Here we have ammonia where we have hydrogen bonds where s and p orbitals overlap, and we have a sigma bond formed by a covalent bond between two hydrogen atoms. When nonmetals interact with other nonmetals, however, they share electrons, effectively giving each atom access to all the shared bonding electrons. Thus, by sharing a suitable number of electrons, an atom can achieve an electron configuration that resembles that of all rare gases. So when an atom share a number of electrons, they can acquire an electron configuration similar to the noble gases. For many molecules composed of elements from the main group, this feature leads to 8 valent electrons around each atom. This observation is the basis of what is known as the octet rule. An atom will form covalent bonds to achieve a complement of 8 valent electrons. So the octet rule is when an atom form covalent bonds to achieve a total of 8 electrons. Rare gas atoms has a valent electron configuration of ns2 np6 for a total of 8 valence electrons. Because it has no p orbital in its n1 valence subshell, hydrogen is an exception to the octet rule and can share only 2 electrons. Atoms with more or less than 8 electrons participate in chemical bond to attain the octet. So atoms with more or less than 8 will form 8 to maintain an octet. For example, like you see, we have 7 electrons, 1 is transferred to satisfy the octet rule. We have 7 electrons as well. 1 is transferred, in this case, 1 is shared, and this satisfies the octet rule. The octet rule only applies to s and p electrons. The basic concept of the octet rule can be conveniently depicted using a Lewis dot symbol. The Lewis symbol helps to keep track of the valence electron, making it easier to predict bonding in molecules. They are particularly useful for compounds of main group elements. So, as we said before, hydrogen has 1 valent electron. It does not satisfy the octet rule. Helium has 2 electrons. It ideally would have to pair with 6 electrons to satisfy the octet rule. Lithium has 1 valent electron. Beryllium has 2. Boron has 3. Carbon has a valent electron of 4. In order to satisfy the octet rule, it would like to acquire 4 electrons. Nitrogen has 5 valent electrons. This would like to acquire 3 electrons to satisfy the octet rule. Oxygen has 2, 4, 6 valent electrons. Oxygen should like to acquire 2 electrons. Fluorine would like to acquire 1 electron to satisfy the octet rule, having a valence electron of 7. So neon has a full octet, so it doesn't like to form bond with other atoms. Molecules that have odd number of electrons or fewer than 8 electrons doesn't usually satisfy the octet rule. So when there are too few electrons, this results in an incomplete octet. So we know that sodium and chloride will form an ionic bond where one electron is shared to chloride, an ion of 2, 4, 6, 7 electrons to satisfy the octet rule in forming sodium chloride molecule. The bond between magnesium and oxygen will form magnesium oxide. As you can see, magnesium has 2 valence electrons that would like to give away 2. Oxygen has 6 valence electrons. So both will give a stable electron configuration of neon, and both magnesium and oxygen will form a stable octet configuration. Lithium and fluoride also can lithium fluoride bond, an ionic bond of lithium fluoride, where lithium will give away 1 electron to provide a stable octet configuration of lithium fluoride. To draw a Lewis structure for an element, we use its atomic symbol and place dots around it on 4 sides to depict the valence electron. So as we go across a period in the main group, the first 4 dots are placed singly around the symbol. So you place them singly first, and then as soon as it's more than 4, then you start putting them in pairs. So the elements in the second period will have dots in pairs. So for example, we have neon, and it would be in pairs because you have a total of 8. And again, these are the metal, the metalloids, and the non-metals. When you do the Lewis structure to identify individual atoms, it's not so significant, but where it's significant is to identify molecules or to pair molecules. So when we draw a dot representation of molecules, we add one more level of symbolism to denote bonds between atoms. A line between 2 atomic symbols represent a pair, a shared pair. So if you draw a line between 2 atoms, for example, hydrogen, say for example, hydrogen is bonded to hydrogen, you draw a line between 2 atoms that would signify the bond. This would basically represent 2 electrons or 2 dots, as you would have here. And so this line would represent 2 electrons, which means that you have 2 shared electrons between each. And this accounts for the valence electron of hydrogen. The Lewis symbol for elements in the first 3 period of the periodic table are shown. Notice the similarities among elements in the same group. Lewis structure keep track of electron involved in chemical bonds. Group 1 elements have 1 valent electron. Group 2 elements all have 2 valent electrons. Group 3 elements, which also include group 13, which is aluminum, and gallium as well, would include 3 valent electron. Group 4 as well as 14 would include 4 valent electrons. Group 5 and 15, 5 valent electron. 6 and 16 would include 6 valent electron. 7 and 17 would include 7 valent electrons. So all the halogens, fluorine, chlorine, bromine, iodine, astatine, these are all 7 valent electrons. The exception is helium, because helium would have 2 valent electron in this case, but all the gases will have 8 valent electron, and the gases are neon, argon, krypton, xenon, radon. When fluorine is part of a covalently bonded system, it virtually always forms a single bond by sharing an electron pair, thereby satisfying the octet rule. A pair of electrons shared by 2 atoms is referred to as a bonding pair. pair. So here you would have the bonding pair as we've shown before. The other paired electrons that are associated with a single atom are referred to as the non-bonding electron or the lone pair. So these would be the lone pair. A fluorine molecule has 1 bonding pair and 6 lone pair. So these would be again the bonding pair, and this would be the lone pair. Most molecules are more complicated than hydrogen or difluoride and will contain more than 1 pair of shared electrons. So for example, like nitrogen, if 2 oxygen atoms share a single pair of electrons, for example, then neither atom has an octet of valence electron. 2 electrons have to be shared in order for you to satisfy the octet rule. We have the bonding pair here as well. So this would be 2, 4, 6, 8, and this satisfies the octet rule. This would be 2 bonding pair, which would be 2, 4, 6, 8. And this satisfies the octet rule as well. 2 nitrogen atoms, 2, 4, 6, 8, which would satisfy the octet rule as well. For diatomic nitrogen, 3 pairs of electrons must be shared to satisfy the octet rule, as we've just seen. Multiple bonding results from sharing of more than 1 electron pair. When 2 pairs of electrons are shared, the rest is a double bond, and 3 shared pairs result in a triple bond. Double bonds are stronger than single bonds, and triple bonds are stronger than double bond. A double bond, although stronger than a single bond, is generally not twice as strong. So here we have the single bond, where a single bond occurs between the hydrogen and the oxygen. Here we have CO2, where a double bond occurs between oxygen and carbon. And here we have the triple bond between nitrogen as well as nitrogen. In the single bond, 2 electrons are shared. In the double bond, 4 electrons are shared. In the triple bond, 6 electrons are shared. And here we can see the single bond that has a bond energy of 346 kilojoules per mole. Double bond will have 602 for a double bond between carbon atoms, and the triple bond would be 835, which means that the triple bond is stronger than the double bond as well as the single bond. The methyl methacrylate monomers contain a carbon-carbon double bond. In the polymerization reaction, 2 of the electrons forming this double bond are used to create a bond to a second monomer unit, as you can see here. The end result is that the double bond in the reactant is transformed into 2 single bonds in the product. Because the energy released in forming 2 single bonds is greater than the energy needed to break a double bond, the reaction to form polymethyl methacrylate is an energetically favorable process. Having considered both ionic and covalent bonding, we can begin to understand the chemical properties of the polymers and ceramic. One key biomaterial is hydroxyapatite, which involves both ionic and covalent bonding. How can we predict which bonding interaction will be ionic and which will be covalent? So you determine which one will be ionic by determining which one is a metal versus a non-metal. So you can recall that the ionic bond is between a metal and a non-metal, while the covalent bond is between 2 non-metals. And this shows the order in electronegativity. As you go down a group, there is decrease in electronegativity. As you go across a period, there is increase in electronegativity. So fluorine has the highest electronegativity. Compared to metals, non-metals are relatively greedy for electrons. Even in covalent bonds, the small size and high electron affinity of many non-metals mean that electrons tend to be strongly attracted to these atoms. The attraction of an atom for shared electron is a covalent bond, and it's called electronegativity. affinity. The attraction of an atom for shared electrons in a covalent bond is called electronegativity. So electronegativity in essence is the attraction of an atom for the shared electron. So the atoms that likes to be attracted to other atoms in which they can share electrons. Unlike ionization energy or electron affinity, electronegativity is not an energy change that can be determined experimentally. Instead, electronegativity values are established by considering a number of factors such as the atomic size, electron affinity, ionization energy, and a scale of arbitrary units that has been chosen. So this shows the electronegativity. It's an estimate of the total number of energy in terms of attraction. The electronegativity will increase towards this direction. So fluorine would have the highest electronegativity. It would decrease towards this direction. So as you can see, francium would have the lowest electronegativity, and on average the S block, the electronegativity for the S block is between 0.7 to 1.57. Hydrogen is 2.2. On average we have 1.3 to 1.6 for the transition metals. The metalloids are between 1.9 to 2.18, and this is saying that there is no data for the gases, but as you can see, the group 14, 15, 16, 17 elements tend to have the highest electronegativity. The higher the electronegativity value, the more likely an element is to attract extra electron density when it forms chemical compounds. Electronegativity tends to increase as we go up a group, decreasing atomic number or across a period from left to right. Thus, the trends in electronegativity are parallel to those in electron affinity. So when separated, hydrogen and fluorine are spherical. The negative charge on the electrons and the positive charge of the nucleus offset each other. When bonded, the more electronegative fluorine attracts the shared electron more than the hydrogen. The electron density shift causing a partial separation of charge. The highly electronegative fluorine atom attracts electron more strongly than hydrogen does. So the two pair form a polar covalent bond. So it forms a polar covalent bond because, as we've said before, polar bonds tend to be formed when the energy between the shared electrons are unequal. So polar bond is when a covalent bond between two atoms where the electrons forming the bond or the bonding between the electrons are distributed unequally. So because fluorine has a higher electronegativity than hydrogen, then this will result in an unequal distribution of bonding between the electrons. The fluoridation of teeth, for example, is one of the earliest manipulations of biomaterials and involved the replacement of an hydroxyl group in the hydroxyapatite to form fluoroapatite. To understand how fluorine participates in chemical bonds from covalent to ionic, a covalent sharing point is to compare the electron distribution around the atoms in a molecule with the electron distribution around the isolated atoms. Because fluorine is the most electronegative element, when a fluorine atom participates in a covalent bond with another element, such as hydrogen, more than half of the electron distribution of the bonding electron pair is associated with fluorine atom. The result is that fluorine atom becomes a center of partial negative charge because it has more electron density than is necessary to balance its own nuclear charge. Because the molecule has one region of positive charge and another of negative charge, the molecule has an electric field associated with it. These two points of positive and negative charge constitute a dipole, and such a bond is referred to as polar bond. So the molecules that is formed from the bond has one region of positive charge and another of negative charge, and the molecule has an electric field associated with it. These 2 points of positive and negative charge constitute a dipole, and as such, the bond is referred to as a polar bond because you have a dipole that is formed as a result of a large positive charge region and a negative charge region, and it's unequal, and that's how you get the polar bond. Because the electrons are still shared rather than transferred, these bonds are called polar covalent bonds. So why is water a polar molecule? Water is polar because oxygen and hydrogen have different electronegativity values. Oxygen has two lone electron pairs that repel each other, and the electron bonded to the hydrogen atoms. This gives the water molecule a bent shape. The oxygen side has a partial charge, the hydrogen side has a partial charge. These two lone electron pairs result in a bending of the oxygen molecule because these pairs repel each other, create a bent structure with a bond angle of 104.5 degrees. The polarity of covalent bonds varies from completely non-polar, as in difluoride molecules and hydrogen. The type of bond formed depends on the electronegativity difference between bonding atoms. The greater the difference in electronegativity, the more polar the bond. The polarity is highly dependent on the electronegativity, and the greater the electronegativity, the more polar the bond will be. At some point, typically when the difference in electronegativity exceed above 2.0, the bond is classified as ionic. So here you have a non-polar covalent bond between two chloride atoms or two chloride ions, where you have the bonding electrons that are shared equally between the two atoms. There's no charges on the atoms. Here you have the polar covalent bond, where the bonding electrons shared unequally between two atoms, partial charges on the atom, and this would be hydrogen chloride. For the ionic bond, you have a complete transfer of one or more valence electron, so the full charges on the resulting ion. Bond polarity plays an important role in several aspects, particularly with regards to biocompatibility. Materials that will be deployed in living systems always interact with those systems. Polar bonds in molecule along with outer wall of blood cells help to allow the blood to interact with water. Those same polar bonds can also interact with biomaterials and influence biocompatibility. So this is basically showing the carbon-to-carbon bond where there is p orbital. It also shows the polar bond and the importance in electrospinning, micropatterning, nanopatterning, bioprinting, and these are all biomedical engineering approaches. And the important thing is the polar or the bond polarity is important in the synthesis as well, in chemical synthesis for photopolymerization and electrochemical synthesis as well. So the Lewis structure represents the chemical bonds and valent electrons in a molecule, as we've discussed before. So to write the Lewis structure, you count the total number of valence electrons in a molecule or ion. You draw the skeletal structure of the molecule. The element written first in the formula is usually the central atom. So if you get a formula, the element that is first is going to be the central atom in the molecule, except when hydrogen is listed first, because hydrogen can never be a central atom because it can only form only one bond. Usually the central atom is the least electronegative. So this is the Lewis structure for H2O. We know that oxygen has 6 valence electron and hydrogen has 1. Hydrogen is a non-metal, oxygen is a non-metal, so you're forming a covalent bond, and a covalent bond is when they share electron. So you have 1 electron that is shared from hydrogen along with 1 electron to oxygen, and this gives us a lone pair which contains 2 electrons on both sides, and this would be 2, 4, 6, 8, where this satisfies the octet rule. And here we have nitrogen in the center because it is listed first for NO3. Carbon has 4 valence electrons. It likes to acquire 4 to satisfy the octet rule. So we basically have 2, 4, 6, 8, 2, 4, 6, 8. for CO2. That would be the Lewis structure. In oxygen difluoride, oxygen is written first and is the least electronegative element, so it is the central atom. So once it's first, it's the least electronegative, it will be the central atom. We write the two fluorine atoms surrounding the oxygen. So the first thing again, the oxygen comes first, it is less electronegative. You find the number of valence electrons, which is 6. We have two fluorine atoms, which consist of 7 valent electrons. So in each case, both you will need 2. You would need 2 lone pairs to satisfy the octet rule. So step 3 in constructing a Lewis structure for oxygen difluoride, you would place single bonds between all connected atoms in the structure by drawing lines between them. Place the remaining valence electron not accounted for in step 3 on the individual atoms. So you would have to identify the atom that would be the center first. Then you would identify the valence electron. In this case, it would be 6 for oxygen, and for fluorine, it would be 7. So for oxygen, it would be 6. For fluorine, it would be 7. So you would place the single bond between the connected atoms. So this would be 2, 4. And then you start adding the remaining valence electron, which would be 2, 4, 5, 6, 7, 8 for oxygen. And we're sharing 1 and 1. So that would be 6. So we have a remainder of 6 for fluorine. So that would be 2, 4, 6. 2, 4, 6. So here we have the Lewis structure for the diatomic molecule oxygen. So this would be the Lewis structure for O2. So we know that one oxygen has 6 valence electrons. So that would be 6 times 2, which gives us 12. So we have 2 lone pairs, which represent a double bond or 4 valence electrons. So that would be 2, 4, 6, 2, 4, 6. Here we have the structure for methane, which is CH4. So the C comes first. It has 8 valence electrons. We know that hydrogen has 1 valence electrons each. So we have a pair or a lone pair of 1, 2, 3, 4, which basically gives us 8, which also satisfies the octet rule. So nitrogen, we know, is a gas. It has a valence electron of 5. So this would be 5 times 2. So you're trying to get 10 valence electron for both. So in this case, you have 3 bonds with each having 1 lone pair. So we have 2, 4, 6, 8, 2, 4, 6, 8, which satisfies the octet rule. And this we've looked at before. Lewis structure for H2O, ideally it should be bent. This is also for hydrogen. The Lewis structure of fluorine, chlorine, bromine, iodine. Fluorine has 7 valence electrons. So the important thing is that when the element has 1 bond, it likes to form 3 lone pairs. 1 bond, 3 lone pairs. 1 bond, 3 lone pairs. When the element has 2 bonds, it likes to form 2 lone pair. When the element has 3 bonds, it likes to form 1 lone pair. So the important thing is when the atoms combine to form molecules, a single bond is determined by 2 valence electrons. Double bond is determined by 4 valence electrons. And remember that the valence electron will determine the bonds that the atom like to form. So for example, the halogens like to form 1 bond. Carbon has 4 valence electrons, so it likes to acquire 4 bonds to satisfy the octet rule. Nitrogen has 5 valence electrons, so it likes to form 3 bonds to satisfy the octet rule. Oxygen has 6, so it likes to form a double bond to satisfy the octet rule. Lewis structures provide us with a convenient way to gain some insight in a molecule's bonding. They don't really tell us much about how chemical bonds might be formed other than through the general notion of electron sharing. In lecture 6, we learned that the best current model of the atom views electron as deionized wave described by orbital. And here you can see an s orbital overlap, s plus p orbital in hydrogen fluoride, and the corresponding Lewis structure below. To explain how the waves or two orbitals might interact with one another, we will need to invoke the concept of interference, which provides a clear contrast between waves and particles. When two particles occupy the same space, they collide. But when two waves occupy the same space, they interfere. This interference may be either constructive or destructive. So an hydrogen atom plus an hydrogen atom in the s orbital provide a destructive combination in the nodal plane, but when the orbitals overlap, you have a constructive combination. In constructive interference, two interacting waves reinforce one another to form a large wave. In destructive interference, the two interacting waves offset or cancel one another to produce a smaller wave or no wave at all. So here we have the simple sine wave that is showing the concept of interference between waves. In the upper panel here, the two identical sine waves on the left are totally in phase with one another, meaning that their peaks and valleys line up. Adding these two waves will produce constructive interference. So when the peaks and the valleys of the wave line up, you have a constructive interference. And the resulting wave will have twice the amplitude of the original wave. In the lower panel, B, the two waves are out of phase. So one up, one down, one up. Combining these waves will result in destructive interference, where the two waves effectively cancel one another and result in a flat line. In quantum mechanical model, electrons are simply one type of wave, and we can picture chemical bonds as an example of constructive interference between electron waves. But for electron waves from different atoms to interfere, they must first occupy the same region of space. This idea forms the basis of valence bond model of chemical bonding, in which all bonds are seen as a result of overlap between atomic orbitals. So the valence bond model states that all atomic orbitals are overlapping, and as a result you can have a sigma bond or a pi bond. So here you have two 1s orbital overlapping. In the case of hydrogen, that would produce a sigma bond. When p orbitals are involved, their more complex shape will lead to different geometries. Using Lewis dot structure, we can show easily that nitrogen, for example, must have triple bond between the two nitrogen atoms. You will have two electrons in the 1s subshell with an electron of 1s2, two electrons in the 2s subshell, 2s2, followed by 3 electrons in the p subshell. So the question is, how do 6 electrons occupy the same region of space without strongly repelling each other? The valence electron configuration for nitrogen is 2s2, 2p3, because 2p orbitals are singly occupied. Overlap of 2p orbital from one atom with a corresponding 2p orbital from another atom should enable bonding formation. Because their shapes, p orbitals can overlap in different orientation. As you can see here, the different orientation of overlap in the XYZ plane. Recall that 3 2p orbitals from any atom can be described as lying along the XYZ axes. Let's assume that two nitrogen atoms approach one another along the x-axis. 2pz orbitals can overlap end to end. This leads to a buildup of electron density along a line drawn between the two nuclei, just as we saw for hydrogen. This type of constructive interference produces what we call a sigma bond. So when 2p orbitals approach one another and overlap end to end, as we can see here, they form sigma bond. So consider 2px and 2py orbitals of nitrogen atoms. As the nuclei draw closer together, the orbitals can overlap in side-to-side orientation as shown here. Once again, the overlap leads to constructive interference. This allows the buildup of electron density between nuclei, and that is crucial to chemical bonding. So the electron density is localized above and below, or in front and in the back of this line. Such bonds are called pi bonds. In the nitrogen molecule, we can envision one pi bond formed by overlap of 2px from each atoms and another pi bond formed by overlap of 2py. The triple bond thus comprise one sigma bond and two pi bonds. So when 2p orbitals approach one another and overlap side by side, as you can see here, they form a pi bond. So this is basically the sigma bond where the orbitals are overlapping, and these are the pi bonds. Despite the obvious conceptual challenges that quantum mechanics poses, we accept the existence of SPD and F. When atoms combine to form molecules, however, the observation note above suggests that often those same orbitals cannot explain the facts. So this leads us to the hybrid orbitals, or the overlap of orbitals, where you have an overlap of S2-3p orbital, an overlap of a d orbital, or dx and dz orbital, for example, and one s orbital with 3p orbital in this case. And this will form a SPXDY hybrid, or SDX hybrid, or SPX hybrid. So we just noted that electrons in p orbitals would be expected to lead to an HOH bond angle of 90 degrees in water, for example, and this does not agree with the observed geometry of the molecule. This leads to the introduction of the concept hybridization of orbitals, which is intended to reconcile the notion of orbital overlap with a wide range of observations on molecular shapes and structures. So a sp3 hybrid overlap in H2O would simply mean that you have one s orbital and 3p orbitals overlapping, and this would be the electron configuration in this case. In the 2s orbital, you have both electrons spin paired, one up, one down. In the 2p orbital, you have one spin paired, one up, one down, and the next two up. So this means that the 2s has 2 electrons, 2p has 4 electrons. At its heart, the idea of hybridization acknowledges the fact that when two or more atoms approaches another closely enough to form chemical bonds, the interaction can be strong enough to reshape the orbitals on these atoms. The simplest stable binary compound formed by carbon and hydrogen is methane, CH4, for which the Lewis structure is shown here. The 3D tetrahedral structure for methane, the bond length and strength can be measured experimentally, and such measurements clearly show that all 4 carbon-hydrogen bonds in methane are identical. Furthermore, molecular shapes can also be measured by observing the rotation of molecules, and such measurements show that the hydrogen-carbon-hydrogen bond angle in methane are all 109.5 degrees. The 4 hybrid orbitals in the methane molecule are oriented along 4 corners of a tetrahedron to minimize repulsion, hence why you have a bond angle of 109.5. 360 degrees divided by 4 would give you 90, but the accurate calculation of the bond angle for methane is 109.5. Hybridization with 5 or 6 orbitals can allow us to explain that some elements form compounds with extended octets, which is more than 8 electrons around a single atom. When only one p orbital is included in the scheme, we form sp hybridized atoms. When 2p orbitals are included, hybrid orbitals are sp2. So here we have the orbitals combined and the hybridization, as well as the orbital geometry of each. So one s orbital and a p orbital would give an hybridization of sp. One s orbital, 2p orbital would give one sp2. One s orbital, 3p orbitals give one sp3. One s orbital, 3p orbitals, 1d orbital will give one sp3d. One s orbital, 3p orbitals, 2d orbitals will give one sp3d2, and these are the corresponding geometries of each. For atoms with valence electron in the n3 shell or higher, hybridization can also include d orbitals. Thus, sp3d hybridization yields 5 orbitals, and when 6 orbitals are included, we have sp3d2 hybrids. So the orbital geometry can have different alignment. For example, based on the region of electron density, a linear geometry would look like a straight line. In this case, you would have one atom in the middle and 2 on the side. So that would be linear. So in this case, you would have a s orbital as well as a p orbital, and the bond angle would be 180 degrees because it's a straight line. So for example, beryllium chloride would be linear because it would have beryllium in the middle along with 2 electrons and 2 chloride atoms, and this would be linear. You can also have a trigonal planar. Trigonal planar would indicate that there is one atom in the center. For example, it would be BH3. So we would have a B in the middle and 3 hydrogen. So we have 1, 2, 3, so 2, 4, 6. And remember that we said that boron likes to give away 3. So we have H, H. So this would basically be the structure. And we could also put it here, B, H, H. This is trigonal planar with a bond angle of 120 degrees. You can also have a tetrahedral in the case of methane, CH4, where carbon is here. So that would be the shape of methane with a bond angle of 109, as we've said before. So the tetra means 4, trigonal means 3. One is surrounded by 4 atoms, one is surrounded by 3 atoms. So one atom is surrounded by 4 other atoms, one atom is surrounded by 3 other atoms. The bond angle in this case would be 109.5. You can also have a trigonal pyramidal in the case of ammonia, which would also have 3. So the trigonal would be 3. We should have 2 electrons here. And octa would be 8. And in this case, you have a bond angle of 90 degrees. For a trigonal bipyramidal, you have a bond angle of 90 to 120 degrees. So again, we have the linear s and the p orbital. The bond angle is 180 degrees. The hybridization is 1 s orbital and the p orbital. The trigonal planar is where one atom is surrounded by 3 atoms. The bond angle is 120 degrees. So that would be 360 divided by 3. It gives you a bond angle of 120 degrees. The tetrahedral, for example, is methane with a bond angle of 109.5, hybridization of 1 s orbital and 3 p orbitals. A trigonal bipyramidal, this is an example. And here we have phosphorus pentachloride, which is an example of a trigonal bipyramidal. So the phosphorus would be in the middle and you have 5 chloride atoms surrounding with 120 bond angle as well as 90. So in this case, you have 3 of the atoms in a single plane where you have 2 of the groups that are also positioned below the plane. And you have the octahedral. So an example would be sulfur hexafluoride, where you have sulfur 6-fluoride atom bond angles between -90 and 180 with an hybridization of 1s, 3 P's, and 2 D's. So although Lewis structure allow us to account for the number of bonds in a molecule and show us the bonding pattern, which atoms are joined together and how many bonds, they give us an incomplete two-dimensional picture of the molecular structure. So if we extend our analysis of molecular structure to 3 dimensions, we need to examine the order in which atoms are joined to one another and also how they are arranged in space. In other words, you need a molecular shape. So the shape can either be linear, trigonal, planar, bent or angular, tetrahedral, trigonal, pyramidal, trigonal, bipyramidal, or octahedral. To arrive at an understanding of shapes of molecules, we need to analyze Lewis structure in more details. A very useful technique for doing this relies on the valence shell electron pair repulsion theory, or VESPA, which states that molecules assume a shape that allows them to minimize the repulsion between electron pairs in the valence shell of the central atom. So here again, number of electron dense areas as it relates to shapes, the electron pair geometry, the ones with no lone pair, as well as 1 lone pair, as we can see here, 2 lone pair, 3 lone pairs, as well as 4 lone pairs. The linear electron pair geometry has no lone pair. Trigonal planar only has a bent 1 lone pair. Tetrahedral has trigonal pyramidal 1 lone pair, as well as a bent geometry in 2 lone pair. Trigonal bipyramidal has 1 lone pair, T-shape in 2 lone pairs, as well as 3 lone pairs linear. The octahedral has 1 lone pair in a square pyramidal geometry, 2 lone pair in a square planar geometry, a T-shape with 3 lone pair in a T-shape geometry, as well as 4 lone pair in a linear geometry. So the Lewis structures emphasize the importance of pairs of electrons around atom, either as bonding pairs or as lone pairs. If we consider that these occupy a localized region of space, we would expect that the various regions would be as far away from each other as possible. These regions are centers of negative charge, and like charges repel one another. Couple this electron pair repulsion with the fact that Lewis structures include only electron in the valence shell, and the origin of the name valence shell electron pair repulsion is apparent. The electron pairs will determine the molecular geometry. The molecular geometry will basically result in pairs that will minimize repulsion of electrons. It should be intuitively clear that only when 2 regions of electron density are present, for example, a linear arrangement would maximize their separation. Most of the bondings arranged we will encounter can be analyzed in terms of 5 basic shapes, as we have discussed before. So the 5 basic shapes are the linear, trigonal, planar, tetrahedral, trigonal, bipyramidal, octahedral. And here we have the number of electron pairs, as well as the number of lone pairs, along with the shape, as well as the ball stick model of a trigonal planar, a bent shape, a tetrahedral, trigonal pyramidal, trigonal bipyramidal as well. And here we also have the seesaw shape, the T shape, linear again, octahedral, square pyramidal, square planar, T shape, and linear. The important thing about understanding the molecular geometry as well as the bonding will allow us to integrate molecular geometry to molecular engineering. So for example, chemotherapy has significant side effects. Drug molecules affect healthy cell as well as disease one. A strategy that uses new biomaterial to deliver drugs exclusively to the desired location in tumor cell, for example, would represent an important advance in biomedical engineering. This must be accomplished with the constraints of biocompatibility. A promising method for this type of drug delivery system uses a material called mesoporous silicon nanoparticle nanoparticles. Silica is composed of a network of silicate units, and those silicate units can form a honeycomb structure, as you can see here. So the mesoporous silica nanoparticles is simply a very small particle with this honeycomb arrangement. Because of the structure, these particles have enormous surface to volume ratio. 1 gram of material has roughly the same surface area as a football field. These pores are the silica, so the mesoporous silica nanoparticle has small pores that you can load small molecules in for drug delivery. And the pores in the mesoporous silica nanoparticles can be used to store drug molecules. Once loaded with the desired therapeutic agent, the pore can be capped with another molecule and the whole nanoparticle is delivered to the target. So this marks the end of lecture 7. Hopefully you stayed with me to the end. Thank you guys for watching, and I'll see you for the next lecture.